All right, hopefully by this time we would have covered in class the basics of simple harmonic motion. We are going to look at one particular system in a lot of detail in chapter 14 on oscillations, and that system is the mass spring system, which you've seen over here. The mass spring system consists of a mass suspended from a spring that could be attached vertically, like in this example, or horizontally. And in either case, the physics of the situation is the same. The only thing that's different between a vertical mass spring oscillator and a horizontal mass spring oscillator is the fact that the equilibrium point shifts when you suspend it vertically. And we're going to look at the oscillations of this system, and we are going to make an interesting analogy. But before that, I want to make clear that everybody remembers the difference between oscillation in general and a simple harmonic oscillation in particular. So a simple harmonic oscillation is the simplest kind of oscillation we can have, and it's characterized by the following. You look at the restoring force in the system and you consider what function that force is of the displacement of the object from equilibrium. So look at this. If you look at this mass spring system, this is its equilibrium position. When it's oscillating, at any moment in time, it's displaced from its equilibrium position, except when it's actually passing through equilibrium. So that displacement, something we call x, okay, is what we are considering when we look at the restoring force over here. So the restoring force of an oscillating system can have any kind of dependence on the displacement. It could depend on the displacement as a square of the displacement, a square root, a cosine, a sine, and so on. But the simplest case obviously is when this is a linear function of the displacement. So it's proportional to the displacement in the first power. Okay? We know that the mass spring system qualifies because we know that the restoring force is the spring force or the Hooke's law force. And in that case, that spring force we know is basically of this form, K delta X, where K is the spring constant. So therefore, the mass spring system is a simple harmonic system. The simple harmonic system can be used to understand eventually all kinds of oscillatory motion, all kinds of periodic behavior, from the swinging of a tall building in a breeze to, for instance, the beating of the human heart. So it's the basis for understanding all kinds of oscillatory motion. So let's look at the mass spring system in a little bit more detail. And what we're going to discover, interestingly, is that there's another way to characterize a simple harmonic motion. Recall that when you studied projectile motion, for instance, or any kind of motion that you did before, linear motion, circular motion, one of the things we are always interested in is where is the object at a particular time, and what is its speed and what is its acceleration at a particular time. So in the case of projectile motion, you have the equations of kinematics that tell you where the object is after a certain time has passed. Similarly, we want to know where this oscillator is, where is the mass at a particular time. So in order to figure that out, there are two ways to think about it. One is formal and mathematical, which we'll cover in a face-to-face class, and the other is more intuitive, and that's what I'm going to concentrate on now. So imagine this mass spring oscillator going up and down between 2 points. So here's I'm going to have a vertical x-axis, which is a little weird, but don't worry about it. This is plus A, minus A. Recall that the displacement from equilibrium, the maximum displacement from equilibrium, is called the amplitude. So our mass is going from here to here, back and forth, like this. And let's say that we start our timer at the point where the mass is at the top of its motion. So the mass is here, and then we start our timer, and that's t equals 0. Okay? So suppose now that we do something interesting. We track the motion of the timer by attaching a pen to it. So imagine the timer has a pen attached, and that while it's going up and down, you are at the same time unrolling a spool of paper. Okay, so this is a paper spool, and it's unrolling at a constant rate. Okay, so the mass is going up and down, the paper is unrolling at a constant rate, and the pen that's attached to the mass is making a mark on the paper. So I hope that you can see, if you can visualize this, I hope you can see that the marks that the pen will make on the paper will look something like this. So we are starting here. So we are starting at plus A. So this is plus A, 0, minus A. It'll start something like this, and then unspool like that. So this is our x-axis, and this is time. And what I hope you'll see is that the marks that the mass makes on the paper, the pen makes on the paper, basically describe what is a cosine function. So in other words, we expect that x should be some function of time that has a cosine dependence. Now it's cosine because we started at a point where the mass was at the top of its motion at time equals 0. Okay? If we had started at a point where the mass was at the equilibrium point, it was passing through 0 when we started the timer, and was on its way up, then we would get, guess what, a sine function of the motion. Okay? And we're going to complete this and see that if this is the amplitude, then this looks like this. Okay? We are going to justify those terms in a moment. But this is the advantage we have over mathematicians, that instead of solving, which is what is essentially a differential equation, we'll talk about that later, we can look to nature to give us the hints as to what this function will look like. What is the dependence of x on time? So it turns out that there are two ways to tell whether a motion is simple harmonic or whether it's a more complicated oscillatory motion. One is looking at the restoring force and seeing what function it is of the displacement. If it's a linear function of the displacement, then yes, that's simple harmonic motion. The other is to look at the dependence of x on time and to see whether that's a sine function or a cosine function. If it's a sine or cosine, that tells you that hidden in that information is the fact that the restoring force is a linear function of displacement, and therefore that is also an indicator of simple harmonic motion. So let's then look at a situation, a general situation, where we're allowed to start the timer at any point during the mass's motion. So wherever the mass might be, if we start the timer, we know the graph could look like, it's starting here or starting there and so on. So what's the most general formula? Because this formula only works if we started our timer at a time when the mass is at the top of its motion at x equals plus a. So in order to generalize the formula, we have to invoke something rather interesting, a similarity between oscillatory motion and circular motion. So I'm going to illustrate that next. So what I want you to imagine is a mass moving in a circle, and it's moving counterclockwise. Let's say it's about here at this moment. Let's call this the x-axis, and let's say that the circle has a radius capital A. It's not a coincidence. That's going to turn out to be the amplitude of the oscillator. So this is plus A, x equals 0, this is minus A, and this object, some object is circling, and let's say it's circling at constant speed. Let's also make the declaration that that speed is equal to 2 pi a, okay, divided by t. And you can see what this is. This is simply this definition of speed as distance divided by time. The distance is the circumference of one circle, 2 pi a, and the time here, the capital T, is the period, which is the time taken for one complete revolution. So this is the constant speed v of the object moving in a circle. Okay, so now I want you to imagine that there's a light shining from this direction, and also a light shining from the bottom like this, so that as this object moves steadily in the circle, its shadow is cast on the x-axis. Okay, so mathematically we'd say we're looking at the projection of the object on the x-axis, but there's a more imaginative way to think about it, which is that imagine that this is illuminated from both sides so that you can see the shadow of this object on the x-axis. So when it's here, its shadow is here. When it's there, its shadow is here. When it's there, its shadow is here. When it's here, its shadow is also here. When it's here, its shadow is here. When it's here, and so on. Okay, and of course, when it's here, then it coincides with the position of its shadow. What I want you to think about then is, let's say I take this eraser and I move it in a circle. Okay, so now I've taken this circle and made it horizontal. If you're looking at this eraser edge on, what you will essentially see, or what it will look like, is that the eraser is actually oscillating back and forth. Okay, so in other words, what I'm trying to say is that if you have an imaginary object moving in a circle steadily at this constant speed, then its projection on the x-axis, or in other words, its shadow falling on the x-axis, is going to go back and forth in an oscillatory motion. So, in other words, if we project circular motion on the x-axis, we get oscillatory motion. And since we know about circular motion, since you've studied it in Physics 1, we should be able to get some idea of simple harmonic motion, oscillatory motion, from what we know about circular motion. So you can see, if we go back to this picture over here, that if we start the oscillator, or rather we start our timer when the oscillator happens to be at plus a and going back downwards, we get the cosine function. That corresponds to the oscillator, this object moving in a circle being at plus a and then going this way. Going this way and then moving this way. So the shadow looks like it's here and then moving back towards the origin. So it's important to establish that correspondence. So let me repeat that. The situation where the mass spring oscillator is at plus A and going back down towards equilibrium is the same as the situation where this object, the imaginary object that's moving in a circle, is at plus A. It's always moving counterclockwise, so it's in this quadrant, the first quadrant of its motion, so that its shadow starts at plus A and then retreats towards the origin. So when the timer is started at the point where the mass is crossing through the origin, let's say on its way to plus A, try to locate where the imaginary circular motion object would be, so that its shadow, the oscillator on the x-axis, would be at x equals 0 and moving towards x equals plus A. So for instance, that means that this object is either here or there. Now if it's here, then its shadow will be at x equals 0, but it would be moving towards minus A. So it can't be in the second quadrant. If it's here, its shadow is at x equals 0, and it's moving towards plus a, because remember, it's always moving counterclockwise. So that means that this is the position of the imaginary object moving in a circle that corresponds to an oscillator where we've started the timer at x equals 0 when it's moving towards plus a, which will give us x equals a sine 2 pi ft. So this means that this analogy with circular motion allows us to make a general case for an oscillatory motion where we start the timer at pretty much any time we feel like during the oscillation. So how do we do that? Well, it's fairly straightforward. Let's say that we start the oscillator at we start the timer at some arbitrary point in the oscillation. So let's say that our oscillator is right here. Okay, so if we look at this projection, that means it's at this position, not quite at plus a, and it happens to be retreating towards x equals 0. Okay, so some random position of the oscillator. This is its starting point. So let's make sure we write that down. This is at t equals 0. The imaginary object moving in a circle is right there, which means the oscillator is here. Okay, now if we look at this motion, let's call this angle is called the phase angle, and it's generally denoted by this Greek letter phi. So this is the phase angle that tells you where did the oscillator start. Now at any other point t, you should know from circular motion that the object would have moved forward by an angle omega t, where omega is the angular velocity. So if this is something that you don't recall, you might want to look at the chapter and refresh your memory of the meaning of angular velocity, and remember that angular velocity is the same as 2 pi f, where f is the frequency of the motion. So I hope you can see from this analogy that that means that the total angle made by the oscillator at any time t after its starting point is basically omega t plus phi 0, because that would be this piece plus that piece. And so if that's the case, then we can readily write down the general form of the equation that represents the position of a mass spring oscillator at any time t due to any starting point. So how do we write that down? Let's do that. And that's pretty much it. That tells us where the oscillator is at any time t after it has started oscillating. And this cosine allows for really any kind of starting point along with the phase angle phi 0. So under certain circumstances, for certain values of the phase angle, this can become a sine function, and so on and so forth. So this is the most general form of the equation for the position of an oscillator. And before we stop, I just want you to think about a couple more things. This is analogous to the equation we found for the projectile motion case, where we had, if you remember, we had x f equals xi plus vi t plus half at squared, which gives us predictive power. That's why we look for these equations, because they allow us to predict that if I kick a football or a soccer ball and I know certain initial pieces of information, then I will always be able to tell where the ball is at any time t, knowing all the other constants in the equation. Now, of course, this is a one-dimensional version, so don't take it too literally. But essentially what we've done is gotten the same situation for an oscillatory system. But remember, for projectile motion, we didn't stop there. We wanted an equation for the velocity, an equation involving acceleration. And so similarly, we want to write down an equation for V, and we want to write down an equation for A. But always we want to also start thinking physically about these, because as you know, physics is not mathematics. And in fact, we only got to this equation for A by using our physical intuition about what the graph looks like. And later on, we're going to verify it and make sure that it does make sense. But before that, I want you to think physically about the velocity and acceleration of an oscillator. So let's look at this oscillation one more time. And I want you to think about where the velocity is 0, where the velocity is a maximum, where the velocity is positive, and where the velocity is negative. And similarly, remembering that acceleration is the rate of change of velocity, which are the points where you think the acceleration is a maximum? In other words, at which points is the acceleration, is the velocity changing most drastically? Because wherever there's a more dramatic change in the velocity, that's where you'll have the maximum acceleration. So we want to develop our physical intuition to make sense of all the mathematics, and this is how we are going to do it.